Good afternoon to everybody who is actually participating in this webinar. And I'm here with my team also. And you know that energy efficiency is not an individual business. It's always, a team works. No doubt I'm the mouth and I'm making the presentation, but a lot of my younger colleagues also work on several topics or several problems where we give the solutions. I work as associate director, and I'm responsible for the activity of a center that is called Center for Research on I joined TERI way back in 90. That time it was Building Energy Group, and we started, and I think it will be very interesting to you that enhancing the energy efficiency in existing buildings. I also participated in energy audits of Shram Shakti Bhavan and other government buildings, which was carried out in 89 or so. Why energy efficiency in buildings? You know that the Central Electricity Authority report, if you look at it, buildings, you can say the almost consume 30% of the total electricity is consumed in a year in India, and industry is just 40%. So building, when I say building sector, it includes both residential and commercial. Residential somewhere around 20 to 22% and commercial 10 to 8%. But intensity is very high, and that's why the focus is on the commercial buildings, and more and more buildings are going to be constructed. So one thing is that because in India, significant amount of energy is consumed in existing stock. This is one reason that, we should be discussing about energy efficiency in existing buildings. The second thing is that by enhancing the efficiency, what we'll do, in fact, will in countries like India, where our demand is more as compared to supply, so we are going to bridge this gap. And by bridging this gap, what will happen? We'll avoid a lot of capacity which are ultimately going to be used in building sector, and that can be used for other sectors. So energy access in India will improve, and also for the duration the electricity is going to be supplied. So this is something you can say is all interrelated. Bridging the gap, energy efficiency, bridging the gap of demand and supply, and providing energy access. Of course, somewhere when we discuss the demand side and supply side, I will focus more on the demand side, not on the supply side. Renewable plays also very important role. I can say the background, and I will start now my presentation formally, and I'll request my colleague to just switch over to the PPTs, right? And what is the best way of discussing is what we feel that, if we can discuss the case studies where the retrofitting in existing buildings happen. That takes into account the technological options, economics, and also when it comes to implementation, the problems or installations, the problems. So I will be presenting 2 case studies today, and also I will discuss that what is new or innovative required when we are identifying the different options for enhancing the energy efficiency, right? Okay. Now we have certain polling questions which we are going to display. You have to reply on that, and probably I will address those in my presentation, so you will get the correct answer of that. My colleague has told me that every polling question will going to take a minute or two, so I'll rather restart my presentation after a gap of 5 minutes till you complete all these polling questions. Now we'll switch on to the second one. Fine. So after all these, you can say the polling thing. I'm going to resume my presentation again. And as I started discussing with you the different load points and how it is defined as load points, that the different energy systems which are installed in a building and how much they consume. Let's say, for example, an office building, and this is the averaged one. You can say not a typical office building, which is centrally air conditioned. Lighting consumes somewhere around 21%, air conditioning 62%, equipment 8%, and others 9%. So roughly you can say that the lighting and HVAC systems or air conditioning system consumes 80% of the total energy consumed in an office building, which is centrally air conditioned. Now, within air conditioning system, for almost 60% of the total energy consumptions, chiller, which is responsible for generating chilled water, which is used for extracting heat from the spaces or conditioning the spaces, consume 50% of that. And pumps roughly 20% or so. So if you look at it, chillers consume 30% of the total energy, lighting 21%, and pumps somewhere around 12 to 13% of the total energy consumption. So that's why these are the three load centers or energy systems, always very important when we plan to improve what we call it, the energy efficiency level or maturity level in buildings. We interacted with different users and clients, and they said that, okay, what options they are looking for are two basically. One, they replace all the existing lighting systems with LED lighting. And if the constant speed chillers are being used, it should be replaced with variable speed, because they are more efficient and significant amount of saving can be achieved. I will present the first case study, and this is something very interesting I share with you. Like, you might have heard about the term energy audit and the organizations which finds out different energy saving options. But here the case was different, because in India, what we have experienced, the energy efficiency market is dominated by vendors and manufacturers. They have their commercial interests, and the options which they bring out, they may not be the optimized one. So one such proposal was submitted by one vendor to a client, and client came to us and said that why don't we do a third-party evaluation of the proposal which is given to them by a vendor, which claims that a saving can be achieved by replacing even the T5 and CFL lighting with LED lighting. So we started not as auditing organizations, but third-party evaluators to check whether this is going to be an optimized solution, along with, you can say, the cost optimizations. This is the way the system, or you can say the lighting system, was appearing. So what in fact we have done, We measured the lighting levels at different work planes. Also, we collected all the information, the type of fixtures, type of lamps, and everything are used. What we have in fact noticed that the lighting levels which are provided at different work planes were not up to the recommended, or rather can say, visual comfort level. And the client also told us that, okay, he will not take up anything which saves less than 40% energy. So it was very challenging for us that, okay, we have to first improve the lighting level to the required visual comfort and to show that the saving can be achieved up to 40%. So this was the challenge of the starting point. And what we found at that time, we contacted that different vendors. We also asked for the technical specifications of their product, and we have done certain selections like 28 watt T5 can be replaced with 40 watt LED. This is a total I'm talking about. But like another one, this is with a cover for the basically open plan office. Then there were certain lighting fixtures used for circulation lighting. So 18 watt CFL can be replaced with 12 watt LED. 28 watt again can be with 18 watt strip of LED, and then the hanging one 28 watt can be replaced with 18 watt. So this is something which we identified that the replacement options of the existing systems. And look at that, all the lighting source, existing lighting source are very efficient, T5 and CFL. And similarly, you can say like halogens, 50 watt can be replaced with 10 watt, and in the meeting rooms, 2 into 36 watt fluorescent can be replaced with 20 watt square. So these were the different retrofit measures for the light. We have also done some kind of lighting simulations. We used all, you can say, the photometric data. If I'm getting very technical, then I think I will explain what is this photometric data. It means that is required for a luminaire whenever we do the lighting simulation and find it out how much light it is going to give at different work planes, or you can say the vertical and horizontal sections. So when we did the analysis at horizontal work plane, we calibrated the model based on our monitoring. And the lighting level which we found 70 to 170 lux. So somehow we calibrated the model that, okay, this the present system is going to give this much light. The problem what we face is that because we cannot calculate the lumen output, which can be fed into the software, and especially in the photometric data, which is going to be used in the software for the lighting simulation. So depending upon the life and lamp lumen loss, we have adjusted this, and finally, based on the monitored lux level, we have done the analysis. And for all the retrofit measures, or you can say that the fixtures which we are going to use here, we have taken the photometric file from the manufacturers and simulated it with the calibrated model, and which what we found that a lux level or the lighting quantity we found somewhere around 180 to 350. So the significant, you can say, the increment as far as the lighting levels are concerned, or the quantity of lighting is concerned. This was done beforehand, before the retrofit starts. The second thing, earlier design, the total load was 38.61, retrofitted, and all this you can say that estimated 21.32 kilowatt. We also done the monitoring using an electrical instrument to find out the average lighting load, because sometimes you know that the total connected load is higher as compared to that what's being used. And this was given to the vendor. All the list of the fixtures and also the load. Then the vendor talks to, this was given to the client. The client talked to different vendors and taken the different cost. So what we found here, it's something very interesting, and I'll share with you one by one. Energy consumption, what we found, it was somewhere around 3,21,000 units. And cost I will discuss later. Annual energy consumption in the retrofitted is 1.73, or you can say the 1,73,000 units. Cost of retrofitting is 22 lakhs. But if you look at the saving of the energy quantity, what we got, it's something around 46%. I mean, this system is going to save 46%. But look at that, the saving cost, because the tariff which is paying is somewhere in the Gurgaon is 13 rupees per unit. And the payback which is calculated was 1.9 years. So it is a 24 hours occupied building with the highest tariff 2 years. Now, depending upon the tariff structure, this is going to increase. And we found that if we are paying somewhere around 7 rupees and our occupancy is only daytime occupied 5 days in a week, then it's something around 8 years. This is something which we really have to look into. Very judiciously, you can say the design system, even though the payback period is 8 years. But the life of these LEDs are stated as 25,000 hours. So if you take the total life, or you can say the total cost, which is based on the life cycle cost, there is always, you can say, the saving, monetary saving, which can be derived. No doubt the first cost is more, payback period is 8 years, but for 15 years or so, more savings can be achieved. So this was my first case study, something, retrofitted. And after retrofitting, the whole system looks like this in the open plan loft. All, you can say, the visual comfort is taken care of, whether it is glare, lighting level, and all, and saving. So the LED, no doubt, can save up to 46%, but because of the economics, still we are and high first cost. We are, many of us, we are not able to go for this kind of options. And we are very hopeful, and I think from tomorrow, some conferences, or you can say some expos is starting in Pragati Maidan, where people are going to discuss new technology about LEDs, probably that will bring down the cost. And also the demand will bring down the cost. And we are quite hopeful that in a year, for daytime occupied buildings, the payback period can be reduced to 6 years. I think, before I start the second case study, I'll ask my colleague to show 2 polling questions again, right? Now, the second case study which I would like to present to you, where we worked and my team worked on it, related to, of course, the HVAC system, which I think we highlighted in the beginning itself, that there are lighting and air conditioning to the major load centers in buildings where significant amount of saving can be achieved. Lighting retrofitting is possible because it's a weather independent system, but because of the weather dependency in HVAC plant, the retrofit or retrofitting is not as common as compared to the lighting. Only when one equipment stops working, then I think people go for the change of that. Otherwise, nothing has been done. But there are people, you can say, they know that if they can optimize or they can enhance the efficiency of their HVAC plant, which is basically the HVAC system minus the fan or AHU fans, significant amount of reduction is possible. This was also like the same thing. One hospital approached one vendor, HVAC vendor, and asked them to submit a proposal so they can reduce their operating costs and enhance their energy efficiency. Some proposal was submitted by the vendor, and then we were approached by the client, and he wanted us to evaluate the proposal. And before that, when we had the discussion, we told them that, okay, what is important is one option is given. We will look at the optimizing the HVAC plant. Brief description of the plant. In this, almost you can say that 5 machines, 5 centrifugal chillers of 800 TR is being used with 2 loop system, primary and secondary. Each loop is having 6 pumps, primary on constant speed, secondary on variable speed. And then the condenser pumps and the cooling tower, they are on the condenser pump, of course, is on the constant flow, but the cooling tower, the VFDs were installed. And if you look at the schematic, it looks like that. This is the chiller, and the primary pump feed into the chiller actually feed into the secondary loop, goes to the building, comes back, and then we have a bypass line. Whatever is the balanced chilled water comes back. So this is the system. When we started our work, first we calculated that, okay, what is the rated efficiency at full load at what we call is the Indian duty condition operating points. We found the chiller was somewhere around 0.66 kilowatt per TR, and the plant means the chiller plus auxiliary somewhere around 0.83. So the design was not bad. Generally, you can say that, okay, it's 0.6. Even if we take what is recommended by ECBC and all, it is somewhere close. Then we noticed that, okay, and I think this is happening in all the plants. We don't have proper instrumentation to measure the chilled water or the condenser water. So we requested the client to install 3 flow meters, or the BTU meters means 1 flow meters with 2 thermometers, so it can actually measure the in and out temperature as well, supply or return temperatures. For primary chilled water line, secondary chilled water line, and the condenser water. Later on, the client said that, okay, because the condenser water flow is the constant speed one, so first you measure the condenser water pumps, and then the same you can actually install on the secondary one. So we said, fine, we'll do that. So this is one of the cost-cutting measures, you can say, which is taken by the client, because the cost of 1 BTU meter is somewhere around 2.7 lakhs or so. But this was done because it's very, very important. And then once these flow meters were installed, we calculated the operating efficiency. And we found that the operating efficiency of the chiller was somewhere around 0.78 as compared to the rate it's 0.66, and the plant somewhere around 0.97 as compared to 0.83. So clearly demonstrated that the chillers and the plant was not operating efficiently. So that makes a case to optimize it. And this happened because of other parameters, especially the in and out, can say supply and return temperatures, flow rates, and all those things. So we thought that, okay, let's identify how we are going to optimize the plant performance. The first thing, what we noticed. So it's the existing scenario, or means before the retrofit and after the retrofit. And the funniest thing is that because the secondary loop was on variable pumping, what we found that the VSDs installed on the secondary line was not operating, so it was operating at 50 Hz. And the flow rate in the secondary circuit of 8,000 US GPM as compared to the primary loop 4,008. So roughly you can say 80%. Or roughly you can say from how much? The primary one? Yes. And a lot of water is bypassed. It is mixed. And the return one is at 11 degree. Supply is 5.6 mixed and 7.8 degree was supplied. Really having a lot of tough time, especially to reduce the latent load in monsoon because they have to dehumidify. And it was a hospital building, so it was working almost, you can say, for around the clock and 365 days. So what we suggested, we manually operated the VFDs, fixed a frequency so that this bypass water quantity is reduced to 908 instead of 3313 USG. And the impact of that. Now this much amount is going to be fixed with 5.6 of this mass flow rate. So the supplied chilled water temperature to the AHU's coil was dropped to 6.4, enough to dehumidify all the air and control the humidity. And operating, instead of operating at 50 Hertz, if it is being operated at 35X or 37 or something we fix, almost you can say that 5 lakhs units were saved. Doing nothing only, you can say, this monitoring and changing the flow rate in the secondary line. So this was the first optimization. See, we balanced the mass flow rate in the secondary. And it was only made possible because of the proper instrumentation or installation of the flow meter. The next, we also felt that because a controller was installed, but was not operating in the auto mode, but it was operating in manual mode. So we called the vendor and asked that, okay, bring it into the auto mode, installed the pressure transducers and other thing. And because there were 3 circuits were there, and generally your controllers, they record the worst one and set the flow rate based on that. So further, there was a reduction in the pumping energy. So what we have done, we measured the flow rate and then corrected everything when in the secondary loop and brought it on, can say, the auto mode. Now this is something very interesting I'll share with you. The effect of wet bulb, or you can say that the moisture content outside. Look at the cooling tower characteristics. This is also a weather dependent system. If my outside wet bulb temperature is 28 degree, what happens, and my chiller is loaded 70%, approach is somewhere around 4 degree. So the water which is leaving cooling tower should be 20 plus 4, 24 degree. And what we found when we measured the temperature which was of the water which was coming out from the cooling water, or you can say the cooling tower, or what we call is the cooling water temperature, and entering into the condenser was somewhere around 28.4 degree. And if you compare, let's say for a same supply chilled water temperature, this line shows the condenser water in 28.4 degree, and the bottom one is at 24, which is possible because of this wet bulb. So we were losing somewhere around 0.05 kilowatt per ton. So per hour we can always work out. So this is the second thing what we have done. We try to optimize the cooling water temperature or condenser water in temperature. And how it was happening, you know that. We plotted the average temperature. If you take the upper curve, the green one, this is the temperature which is coming out from the cooling tower, and this is the ambient temperature, ambient wet bulb temperature. What we noticed that, no doubt, from January to May, and after again you can say from September to December, the wet bulb was low, but the impact of that was not seen on, you can say, the temperature which is, or water temperature which is coming out. And then we had discussion with the maintenance team. They said that, okay, they only look at that, okay, the temperature of the condenser water in, and the moment it comes down to 28, they switch off these fans. And if you remember a graph I showed you, that was the chiller one, lower the condenser water in temperature, better is the efficiency. We worked out and we said that, okay, in order to maximize this temperature, or what we call is take the advantage of wet bulb depression, more cooling towers need to be operated, and it should be operated in this fashion. But what will happen? If I'm operating more cooling towers, my consumption in cooling tower will increase. But on the same hand, my consumption in chiller will come down. And if the net result is saving, I think this is important and we should do it. We found that the saving, just by, you can say, lowering the cooling water temperature, it is possible to save 1.5 lakhs of units every year. Second optimization we have done, we modified the operation schedule of the cooling tower fans. Now, in the constant speed chiller which was installed there, and when the client interacted with the vendor, he simply suggested that, okay, you replace the 1 or 2 constant speed chillers with variable speed chillers. And you know, the 900 TR, if you take into consideration, one chiller is going to cost somewhere around 1.2 crores to 1.5 crores. And depending upon, let's say the same case, 70% loading, IKW per TR, or you can say the efficiency is 0.55. So roughly the constant speed chiller will take somewhere around 310 kilowatt. Now this is the curve of the variable speed chiller. So this is the difference, you can say, that it will come down to 0.45 at 70%, and then you can say the same condenser water in temperature and all. And the variable speed chiller will take only 250 kilowatts. So there's a reduction, you can say, for this particular case, 310 to 250 means 60 kilowatt per chiller. So when we worked on it, we have taken the hourly data from the chiller logbook and worked it for each hour and calculated the total saving. And we found that, okay, if we can make two chillers working as can say the variable speed chillers, then the saving is going to somewhere around 3.4 lakhs, depending upon the percentage loading and the ambient wet bulb and other things. Now here, when we interacted with vendors, what we found that there are certain models, especially of higher ratings, where the VFDs can be installed on the existing constant speed chillers, and the cost of those VFDs are not high. And then as far as the efficiency is concerned, it remains more or less same as a new variable speed chiller. The same actually was asked, and I'll show you that these are the reduction, you can say, from, showing that, okay, this is the condenser water in temperature, but this may vary depending upon the wet bulb. This is something interesting we found, that if VFDs are installed on one chiller, it is going to cost, and the cost was given to the vendor, by the vendor to the client. So we have taken this data from the client and worked out that, okay, what is going to be the payback period. It was just 1.85 years. And it is, I think, economically very viable, because if you look at the tariff, it's just ₹8. And optimization, if we take into consideration what we have done here, the total saving, when I said the total in a saving, it means as against the energy which is consumed in the HVAC plant was somewhere around 40%. These two almost, you can say, free. And third, the annual, you can say the investment was required of something around 50.2. 14%, you can say, only in with this, you can say that first cost or investment of 50. Now, what actually I'm recommending here, and I think it is for everybody who is attending this webinar. Now, you must have interacted with the people who are doing energy audits and other things. They're also the third-party evaluators. But what is important for them, or you can say, what is important to them, to find out different options and submit it. They don't work as a third-party evaluators. It is always good that, okay, all these independent organizations who are not manufacturing any device or equipment, or there's some commercial interest is required, they should work along with the vendor for the client to give them the optimized solution, which is going to get the maximum energy saving as well as the at the least cost, which is, I think, very, very important. And if they can also develop the monitoring or measurement and verification protocol, so this can easily be demonstrated to the users, because users, they have more confidence on, you can say, the third party evaluator as compared to the vendors when it comes to the HVAC, because it's the most complicated system. Apart from that, the financial model. Look, in our scenario, we have two types of buildings: government, or what we call is the where there is no approval is required, and then the municipal buildings where approval is required. A lot of corporates, they actually come under this municipal buildings. They have taken certain decisions. They have come up with a policy that they have to reduce 10%, 14%, and they're looking for the viable options, or which can be replicated also. Sometimes they also require a sound financial model so they can replicate it. So if in India we have three things: one, third-party evaluator, robust measurement and verification protocol, and a sound, you can say, the financial model. I think next decade, there's the energy efficiency, because it is also supported with the government policy, will definitely bring the maximum benefits to the users. Thank you, and here I stop, and if there is any specific questions you can give, right? I'll love to answer them. Thank you. Hi, Sandeep, this is Pradeep, and I'm going to take up your question, which is related to the VAM, right? Hello?
Yeah.
Okay. The reason I tell you in TERI, we are more into what we call is the action research, right? Not, you can say, the R&D and basic research. This is number one. So we go to the field and find out what the market demands, come back, then work on it and give them a solution. Now coming to the absorptions, what happened in India? If you look at the history, first we gone for HSD fired, then now the gas fired is there, right? Or you can say also in CHP or tri-generation, we are using it with all these hot gas emissions, right? But we are not directly into the R&D, right? We are also thinking of using this VAM machine, using the hot water-fired VAMs, right? Where the hot water is going to be generated by the solar hot water system. This is something currently we are working on, and we are planning to use a simulation software where we can see that the advantage and disadvantage of that. Mukesh, when it comes to the subsidy, right, the government's stance is very clear when it comes to the central level, that because they think that it creates a win-win kind of solutions if you take the total into account, right? And let's not only see a CFL with LED. I think what is important is the overall application of LED, whether it is street lighting or you can say in the indoor lighting for task or non-task purposes. But there are certain policies which are available at the state levels. Like in Delhi and all, we have, the government sold it at the subsidized rate. We heard that, okay, the government is coming with a policy where only the lamp, I'm not talking about the other fixtures and assemblies, only the lamp, because the other issues are also, and your question is very relevant in that, okay, when we talk about CFL to LED, it is point to point, and CFL, you know that, okay, people say that it contains mercury and all if it is going to be used for replacement of incandescent. I think there's all the problems and all. Government is looking from a different point of view, that because the life is going to be almost, you can say, 25,000 hours. CFL now you can say 6,000. So what happens even if it is distributed free of cost? People, the moment it gets used, people go back to the incandescent. But with this, people will be using for, can say, for longer time, maybe for 10 years and all. And that's why when we look at that, something I discussed about the avoidance, capacity avoidance, and other things which are the priorities of the government. But all these incentive or subsidized item at the state level, not at the central level. So it's very difficult to say that, okay, it is being done. Which one? Energy saving items. Yes, I'll tell you that because what happens when I was explaining you the consumption wise, Mukesh, I'm actually answering your question. No, which one?
It's a common question.
It's a common question, right? You know that, okay, we have two types of approaches, right? One, what we call is the equipment, and other one is what we call is the design. Equipment is that, okay, you buy efficient equipment like air conditioners, refrigerators, CFL, or you can say LED or fan, energy efficient fans and all. And Bureau of Energy Efficiency have already come up with, you can say that, standard and leveling programs where they have identified the efficient products, right? We cannot say that straight away that how much building design is going to reduce the heat ingress, or you can say the heat entering, because that is going to downsize the AC. But in India, you must have found it that, okay, the lowest capacity is still 1 ton. I think they have introduced a couple of years back 0.75 TR, but that was not very successful. So 1 ton machine, but operating cost, of course, is going to be less, and this is the more efficient. By the time you will find that, okay, and I'm actually answering your question in reference to the urban or semi-urban localities. Because what happens, the maximum saving, maximum consumption in the air conditioning, like I'll share my example with you. November and February, my energy bill is less than 1,000, but in May and June, I'm using 2 ACs, is somewhere around 14,000. So this is something, you know, that the difference of the AC. If we have efficient air conditioning system, and probably you must have heard that the inverter-based technology is being launched. And a lot of people are claiming that 70% energy can be saved and this much energy can be produced and all. But still, it is not labeled. No doubt, the Bureau of Energy Efficiency is trying. And once we come up, I'm sorry, standards for the ACs with inverter in India, then I think it is going to be, but people have already started buying it. I would definitely, along with my all teammates, like to thank everybody who attended this webinar. I have with me Ashish, Tarun, and Sandeep, Ashish, you know that we are especially thankful to him because he organized everything. Tarun Tarun works in the field of lighting and TERI and air conditioning both, and Sandeep is our expert on heat pumps. I'm really very, very thankful to you that, okay, you have taken your time and attended this. Thank you very much. And hopefully we'll meet again because we are also want to discuss several issues. And please somehow understand the retrofits measures, the difference between retrofits and the new design. New design, I think we can handle many things. When it comes to the retrofits on existing buildings, the constraints are more. So we'll discuss about the next time we'll meet the geothermal system. Thank you.